AM2D and Monash University Clayton wish to acknowledge the people of the Kulin Nations on whose land we are gathered today. We pay our respects to their elders past and present, and I ask those of you online to pay respects to the traditional owners on the lands which you are situated. We are very, very excited to have our guest with us today. I'll just do a very brief introduction and then hand over. Associate Professor Noushin Nasiri is the head of the Nanotechnology Laboratory at the School of Engineering at Macquarie University. She is the head of, the Deputy Director of the Smart Green Cities Research Centre, also at Macquarie University. New South Wales Cancer Institute Fellow and Chair of the IEEE Women in Nanotechnology Council. Noushin is also one of Australia's 2021-22 Superstars of STEM, the recipient of the New South Wales 2019 Young Tall Poppy Science Award, and has done 3 TEDx talks and a variety of other media, and I recommend those TEDx talks. They're really, really good. Her research focuses on design and fabrication of nanostructured materials, miniaturized sensor technologies, and wearable electronics for personalized and preventative medicine. I hope you enjoy Noushin's talk today, and we are very excited for it, and thank you very much. Noushin, over to you.
My pleasure. Thank you so much, Phil, and thanks for coming. Thanks for inviting me. It's actually my first talk at Monash University. Today I'm going to give a more general view of what my research team is doing. I try to not go into too much details of each of these projects, but feel free to reach out and ask any question if you're interested in a particular project. In our team, I would say one expertise that we have is nanomaterials fabrication. I'm a materials scientist, materials engineer, so it's always a struggle how you introduce yourself. I've done my undergrad and master's in materials science and engineering, and then my PhD in nanomaterials. And I'm very passionate about using a wide range of nanofabrication techniques to fabricate different type of materials, and then different type of morphology, structure, and then of course, because I'm an engineer, I'm also passionate to use them for a wide range of application. So today, and usually, of course, there is a very good interest in my team to use them for a wide range of sensing application, but we try to not limit ourselves in terms of sensing. Today I want to focus on one particular technique that we're using, which is flame spray pyrolysis, and because that is the very more advanced one, and also we can design and fabricate a wide range of structure. So we use them we can fabricate them in different on the top of different substrate. You can use like a plastic, you can use ceramic, you can use glasses, and then you can also modify or design a different structure, mainly very porous structure. As you can see on the a top image B, is 98% porosity, the film that we grow, and that's why we have this interest of using them for sensing application, because a huge surface to the volume ratio because of that pores. But as I said, it's not only limited to sensing application. I've done my PhD at ANU on UV photodetectors. Started like almost 12 years ago, but then we expanded it into pressure sensors, gas sensor. I've done a lot of work in catalysis, designing them as a hydrophobic or hydrophilic surfaces, for example, hydrophobic one to repel water. And also I've done some work on tissue engineering, designing a surface that we can grow cell on the top of the surface, or designing some kind of a membrane for guarded bone regeneration. I have 2 dentists in my team that they're particularly interested in that membrane. But today, as I said, I'm gonna mostly introduce this technique. Is one of my favorite toys that we have in the lab, is a flame spray pyrolysis. So this is what is happening over there. You can put your substrate. It can be any substrate. You put your substrate on a water-cooled substrate holder, and we have also different type of water-cooled substrate holder. The one that can rotate, the one that can move back and forth. So you can manipulate a little bit on how you want the coating to be deposited on the surface. But what you see in the middle is our substrate. You can also change the size of the substrate, put it there, and then it is one of the, I think, the most efficient machines to fabricate metal oxide. And it's kind of pretty simple. This is how it works. If you, for example, this is an example for zinc oxide, but you can think about any type of metal oxide. If I want to make zinc oxide, I need a precursor which has a zinc source, and then I need a solvent. Both of them should be flammable, and then the solvent is just to kind of carefully define a concentration of the zinc atoms into the liquid precursor. Then I purge them through the system over there. Then there is a pilot fire over there, but then the middle fire you see in the middle, which is a very obvious one, that is the precursor being injected into the system, atomized using this oxygen. When the droplet is coming out of the needle, the oxygen with a high pressure hit the droplet, atomize it into extremely tiny droplets, and then the combustion happen inside the fire, then the nucleation happen, and then by the time that this precursor is coming out of the fire is actually, you have a lot of metal oxide created over there. So then this is hot here, it's very cold on the top, so then the metal oxide nanoparticles, they work as they are aerosols. They go up and they sit on the surface, and then they move based on the Brownian motion, and that's why you end up with an extremely porous structure. And then you can just do exactly the same thing with any type of metal atoms you want. You put tin, you end up with tin oxide. You put titanium, you end up with titanium dioxide. And then if you put noble metal here, you will end up with noble metal because they're not going to be oxidized. So you can create gold nanoparticles or palladium or platinum nanoparticles by the same technique. So I'm going to present very recent work since 2023. I don't want to go very back. One of the good things about this machine is that we can change a lot of parameters over there. One of the parameters is height above the burner. We can simply put the substrate closer to the fire or put it very far from the fire. And just by changing the height above the burner, we can change the structure significantly. You can see that 8 centimeter, that is the type of a structure, of course, is a little bit tilted. What you see over there is a bit tilted substrate and also the film. 9 centimeter is a bit more porous. You go to the 14 centimeter, you can see how fluffy the structure will be. And then if you go for 20 centimeter above the fire, then the structure will be extremely porous. So then for some sensing application, you might prefer a bit higher height above the burner because it gives you a way more porosity. But then if you dip this one into the water, the film will collapse because it's not strong enough. Then if you need something that should handle a little bit harsh environment, then maybe you would consider going to be a bit lower height above the burner. But this is one of the parameters that we can change. There's a significant number of parameters: the pressure of oxygen, the concentration of the liquid, the feeding rate of the liquid, and then it's completely different structure every time. You can literally create a wide range of structure just by changing each of these parameters. One of the work I wanted to present is my former PhD student. He's still in the group as a postdoc. So what he did, he put his substrate at 12 centimeter, which is considered a quite strong film. This film, we got 18.5 micrometer of zinc oxide on the substrate, and this happens after only 100 seconds spray. So it's a very fast technique. You put your substrate there, 2 minutes later, you got 20 micrometer of a film deposited on the substrate. So that is a structure, but then what he did is, from D to G, he put a tiny droplet of ethanol, not directly on the film, but on the side, and let the ethanol to be sucked in by the film. And then we've noticed, and this is the ethanol going into the film, and we noticed that the structure significantly changed just by, and that one is 5 microliter of ethanol. Well, and I'm going to tell you why this is really interesting. So what I can show you is that the recorded video under the microscope, that how ethanol is actually changing the structure. So what you see right now is the structure from the top view. And now that ethanol, 5 microliter of the ethanol is coming. First, he kind of loses a little bit of a focus because the film shrink a little bit, from 18 micrometer down to maybe 16 micrometer. But now the ethanol is evaporating. And while the ethanol is evaporating, the capillary force of the evaporation is pulling this nanostructure towards each other. And you can see that that structure, from a very continuous, homogeneous structure, now we are creating these clusters on the top of the surface. So now it is evaporating. So he's going to focus on the top of he called them nano macro clusters, NMCAs. And then he's focusing on the top. And then he's focusing on let's say he's focusing on the valley, and he's focusing on the hill to show you how the structure is different. So why this is interesting? Okay, so the top one, the top row is a flame-made one. You put your substrate there, spray by flame, top view, high magnification, 8-degree tilted, and that is your structure. You put 5 microliter of a droplet, 1 minute later is dried out, and that structure is changed into this one. All these, I would say, volcanoes maybe, or to me sometimes if I don't have a good day, to me is a dead forest, like it's a forest and then you killed all the trees. It depends how I started my day, but that structure is changed into this structure, and you see the electrodes at the bottom. And this structure is now patented by Macquarie and is licensed by 2 companies because it gives us a significantly higher performance in terms of sensing application. We believe 2 things happens. In the macro scale, the clusters from the flame, and let's say there is this liquid between 2 clusters. I'm just going to quickly go back. The clusters I'm talking about are these ones here. So there's like a cone-shaped structure which is coming from the flame at a certain parameter. And those structure, when we put a droplet, the liquid goes between all this structure. And now imagine the liquid is evaporating. If the liquid is evaporating based on the capillary force, based on the Laplace pressure, it's pulling, at least this is what we think, it's pulling these 2 clusters, not only 2, let's say like 5 of them, let's say 10 of them, it really depends. It's pulling them together and it's creating that forest structure over there. At least this is what we think. This one is what happened in the macro scale, but in the nanoscale, the same thing happens. So let's say there are nanoparticles, and because by flame, they just move based on the Brownian motion. So when they sit on the substrate, there is no significant contact between the nanoparticles. They just sit physically on the top of each other. And then when you want to test them as a sensor, the electron cannot easily move from one particle to the other one because there is a boundary here. That's why every time we make the substrate, we make the film, we have to put it in the oven and we have to do the annealing to make sure that there is a necking happen between the particles. But this technique, we don't even need to do the annealing anymore. So the liquid, again, this is what we believe. We believe that when it is evaporating, the liquid is also sitting in the gap between the particles. And again, the same scenario as this one is valid over there. That liquid now, which is ethanol, evaporating, and when it is evaporating, it's pulling these 2 particles into each other, and it's cold welding these 2. So we calculated, based on the size of the particles and the droplet, we calculated what type of force or pressure is applied on that particles. It is in the scale of gigapascal. And the gigapascal is enough to kind of weld, at least in this case, zinc oxide nanoparticles into each other. So doing this, we can skip the annealing process, which means you can do it on any type of substrate. You can do it on any type of nanoelectronics. You don't need to do the post-sintering process in order to make your electrical connection happen. So what I'm going to show you here is that we use it as a UV sensor, which is one of our applications. So the bottom one in the black is turn on, UV on, UV off, UV on, UV off. And you can see the one on the black is before we put 5 microliter of the droplet. And the one in red is after we modify it. Both cases is exactly the same sensor and it's exactly the same material because ethanol is a pure ethanol, evaporates. So you end up with 2 zinc oxide, but it is before and after process. And of course, it's a bit faster in terms of how it's responding, which we believe that is because the electron can move much faster. The other property that this film is giving us is that now the film is very strong. And now if I add another droplet, if I have a much larger droplet, so now I have this structure, and now I'm going to send the second droplet coming to the system, and it's not going to change anything anymore. So now this film, you can dip it into the water, you can leave it into the water, and it's not going to be damaged by any liquid anymore because the first droplet, which is perfectly designed in terms of size and in terms of evaporation rate, creates such a stable structure that the second droplet is not really damaging the film anymore. And as you can see, the sensor is very stable. This is just a chunk of the test that I cut it from the sample, but we could run it for like weeks, and then every time on and off, you actually end up with the same results. So that was the main discovery. But then it gives us the opportunity to add anything we want into the system. So the flame spray pyrolysis is great for metal oxide. But for example, if I want to make a composite, if I want to add carbon nanotube, there was no way for me to add carbon nanotube, because if I wanted to add carbon nanotube into my system, it will collapse. But doing this, we actually have the first droplet changing the structure into this structure. And then in the second droplet, which is not going to change the structure anymore, we added carbon nanotube, and the carbon nanotube goes there. And then now we have a composite. And you can think about any type of other materials that you cannot fabricate by flame spray pyrolysis, be added into that ethanol droplet, and then be added into the film. And of course, we added carbon nanotube to make sure that, for example, sometimes the clusters might not really connecting with each other, but with the carbon nanotube, we could actually create this very great, I would say, bridges between this cluster to another cluster. And this one was selected as a cover photo of applied materials and interface. But we also, because of the conductivity of carbon nanotube, we also got significantly higher, again, electrical signal or a sensing performance from our sample when we added carbon nanotube. And then, as I said, it can go on and on. We can add anything that you want. In this work, which is not published yet, Reza added P.PSS as a polymer. Again, we could not add polymer into the system before because it will damage the structure significantly. But now, after modifying it, the second droplet could carry whatever material that you want. And as you can see here is that this cluster is beautifully connected with the P.PSS, which is the conductive polymer, to the other one, connected to the other one, that one connected to the other one. And of course, there is a lot of optimization in order to get to the point that it is not too much of polymer. And then we have all these clusters communicating with each other, both from the very, very bottom, this is a substrate, and also from the top with a very optimized thin layer of polymer. As you can see here again, it was actually everywhere on the film. So this cluster connected with this one, connected with that one, connected with that one. So it's all connected with each other, significant improvement in terms of communication, electron transport and communication within the film. Then another question came to our mind was that which one is playing the key role in making the film better? The clusters combining and joining each other and creating that volcano, or the change that is happening between the nanoparticle. So this time what we did, we actually used vapor. We didn't use the droplet. We only used vapor. So what the student did, so this is the sensor, like the film. So that's a glass substrate. And that has electrode. It's coated by flame, which is this one here, F. It's coated by flame, and we put it in just a Petri dish. We created a chamber over there. It's a Petri dish, and we put 6 droplets of 0.5 microliter of 1 mole acetic acid, which is quite similar to vinegar. It's a very diluted vinegar. And we close the lid. What happened here is that we let these droplets, which are significantly small, evaporate inside the Petri dish and create a vapor-saturated environment inside the Petri dish. And now we remove this sample after 5 minutes, let it dry, 10 minutes, 15 minutes, and 20 minutes. And we see that structure changed again because it's been exposed to a tiny, tiny concentration of acidic vapor. Again, the hypothesis we have is that inside the chamber, we have a lot of droplets. When I remove my sample from the chamber, the droplets are already sitting here, condensated on the gap between 2 particles. And now they've been exposed to atmosphere. They start evaporating. And by evaporation, the same scenario is a Laplace pressure is pulling these 2 particles, and we kind of created a great gap. So what I'm going to show you is the video. Let me pause it first. So what you see here this time is a much bigger sample. So this is just a glass substrate. The foggy layer you see in the middle is that zinc oxide film. And because it is very porous, this time the HAB is 30 centimeter, because we cannot put a droplet on the HAB of the 30, even the droplet on the side will wash away the film. The film is extremely fragile. The black one is just a tape at the back, and then you see 3 droplets inside the chamber. So what you see, you're actually looking at from the top view, and is a time lapse, so it's a kind of a very fast one. What I want you to pay attention is that how transparent it is at the beginning, and this is 15 minutes exposure, and I want you to have a look at how the transparency is changed after exposure to 15 minutes of 1 mole of acetic acid, which actually is only 3 microliter if you combine the droplets. So you can see that the transparency is changing significantly, which we assume that this is happening because the film is shrinking a little bit, and now the porosity is going to be less than what it was before. See how significant the transparency change over 15 minutes. So I'm just going to quickly, so this is where we started. And then this is where we ended, which again, the same scenario. I'm not going to show you the SEM images, but we actually saw that the particles merge into each other and the film kind of shrink a little bit from 7.5 micrometer to somewhere around 4 micrometer. And of course, again, it was selected for the cover photo of the small. Okay, so this is about the structure, but then another group of my research team, they are more into the electronic side of it. They really wanted to make the sensor out of the take the sensor out of the laboratory and make a device out of it. So what I'm showing you here is the 3rd prototype. The first 2 prototypes are very ugly, I would say. Even this one, there is an error here, but we managed to just add a extra wire over there and fix the error. But anyway, these researchers in my team, they are more electronic people, so they can design PCB. So this is the same sensor I showed you, which is on the top of the. So this coating layer, the foggy layer over there, that is a zinc oxide, a modified structure of zinc oxide. And what you see here is my student holding a UV torch, and he's holding the UV torch, getting it closer, and then they also not design, but kind of, fix this app that it can show you what is the UV index. And then later in the test, they realized that the performance changed a little bit based on the humidity and temperature. So then they added the humidity and temperature sensor embedded into the PCB, and they calibrated the sensor signal based on the temperature and humidity. And then you can see all the live data, and then you can also go back and review how much UV you've been exposed to, what level of UV at for how long. The project, because I'm on the 3rd year of Cancer Institute Fellowship, so this project is funded by Cancer Institute. That's why since 2023, majority of the work that we're doing is actually UV sensing, is because of that fellowship. And as I said, that's the interest. I have my magic box with me here if you're interested. But different type of student, they are interested to design this device in different I would say, maybe in terms of the end user in different design. So for example, in that design, there's no communication with the app, but there's an LED. The color of the LED changes based on what is the UV index. So start with green. If you go a bit higher, UV index, yellow, then orange, then red, then purple. So that's how it's communicated. There's a SD card embedded. All the data is in the SD card. They're also interested to see if they can do it as a kind of a flexible substrate. There's also this student who was interested to know if they put it on a drone and they set it up and down, whether they kind of get impact from the pressure or the altitude, and if the sensor can perform at different height or not. That's why that device is designed. So that is the cover everything, almost everything. So from now, I'm just gonna go slide by slide to other applications that we use, kind of similar technologies, but in different applications. We use them for gas sensing. They are highly porous, as you can see over there. In some cases, we can even detect, I don't count these two, but I can say that we can detect 10 parts per billion of a gas, a target gas. And that's why we have a significant interest from industry. Particularly this one, we have 3 different actually four, oh yeah, three. We have three different projects with Accent since 2020. They also funded a part of my ARC Industry Fellowship, which I'm going to start from January. They're also part of ARC Industry Transformation Hub for Molecular Bioscience Point of Use, which is led by Latrobe University, and we just launched it this January. We also have a PhD student. They funded one of my PhD scholarships. So what they're interested in detecting pregnancy in cows using their breath. They've done this before. They have this bag. They have a device, because with human, you can ask them nicely, can you breathe onto the sensor? And they do it for you. With animals, you have to have a device that can capture the breath. So they have this device. They capture the breath into the bag. They take it to the laboratory. They do GCMS. They figure out what is the biomarker pregnancy in cows. The current technique is very invasive. The veteran has to put their hand inside the animal, and then it's like the animal get upset, kick the veteran, either the fetus die or the veteran. But and also it's quite a late detection. So someday between 30 to 45 days after insemination, they can figure out if the cow is pregnant or not. And for the farming industry, that's a very, very slow process, because if the cow is not pregnant, then they kind of wasted 40 days of their time feeding the cow on the farm while the cow is not pregnant. With breath, they can detect it after 18 days, which is a significant improvement. The problem was they did not have the sensor. Every time they have to capture it, go to the lab, do the GCMS, and see whether the cow is pregnant or not. What we're doing is that we're embedding the sensor inside the device, so then they can do the in situ test to see whether the cow is pregnant or not. Another company, again, we have three projects with them. This company is interested to know if the bees inside the hive, they are stressed or not. And also they are interested to know if the queen bee is still alive or the queen bee is dead. So currently what they do is that they have, like, let's say 1,000 hives, and they go there after 4 or 5 weeks, because that's the life expectancy for queen bee. They open the hive one by one to see if the queen bee is alive or not. And then if it's dead, they replace the queen bee with a new one, and then they have to go back in 1 week time to see if the colony accepted the new queen bee or they killed the queen bee. And then every 100 hives, based on their statistics, 8 of them will kill the queen bee. So you can actually see it's very not really efficient to go and check 1,000 hive and figure out only 80 of them, the queen bees died. So what they want a sensor that can detect the pheromone which is released from queen bee and tell them whether the queen bee is alive or the queen bee is dead. Also, the pheromone that the bees release if they are under stress, to see if they are healthy or if they need a little bit of attention. Moving forward, we do a lot of hydrophilic surfaces. Again, this is the same nanofabrication technique. You can quote that is an Australian dollar, and that's in the water, colored water. So you can see that the bear coin is just water cover the surface, but the coated one, regardless of if it's manganese oxide or titanium dioxide, it can repel the water up to 5 milliliters. So, and of course, it will have a lot of application in terms of the self-cleaning, and you also have application in terms of the solar panels get dirty, and then there is a lot of hard work in terms of clean them. But yeah, if you have that coating on the surface, transparent, then you might be able to actually clean it using this coating. Okay. Again, the same coating has an application, could have an application in terms of anti-corrosion, anti-icing, as you can see in this video. By the way, these videos are not mine. They are like stolen from YouTube. But you can actually coat different structure, use them as an anti-coating, an anti-icing, and anti-corrosion. Another work that we've done, again, the same coating, but this time just change the coating from, let's say, zinc oxide, titanium oxide. This time we change it to hydroxyapatite. And then we create the hydroxyapatite coating on the top of the implant. And then because it is extremely porous, this is for cell growth. When the cell sit on the surface, then they start developing all these filopodia. and then they can actually communicate in a nanoscale with the surface, and they can bond, they can grow, and they reach out to each other, not from the surface, but also from the very, very deeper layer into the film. And then that create a significantly high adhesion of the cell to the surface. We change the porosity. As you can see here, this is a spin coating of the same particles. A spin coating, the communication between the cell and the surface is, I would say, is in the macro scale, but you can actually see that here, the communication, they could grow not only on the surface with significant growth, but also on the deeper layer. Two of my students working on a membrane is a guided bone regeneration membrane. They wanted to separate the gum from the cavity in the bone, and then they can, so the membrane is made of polymeric nanofibers using electrospinning, but we can add a lot of different type of materials into the fibers used as a growth factor, let's say, and then they're going to be released during the time that the membrane is separating gum from the bone to help the bone to grow faster. We also use them for example, energy, and also for catalysis, for electrolysis. This is one of the recently published work that you can even use a carbon cloth. That was a little bit tricky because they're quite sensitive to temperature, but we managed to deposit silver nanoparticles by flame on the carbon cloth and then use them for electrolysis project. These are some of the other works. Not only we make the zinc, the metal oxide, but then we can also convert it into MOF. I'll give you one example here, but you can actually think about any other example. So we made zinc oxide. We expose it to the vapor of the ligand, which is relevant to the ZIF8, and then we convert the zinc oxide nanoparticles into ZIF8. If we expose it to a large amount of ligand, and I'm large, I mean like one gram, then you leave it long enough, the entire zinc oxide will be converted into ZIF8, but you can do partial conversion as well. What we did, we actually created a mixture of zinc oxide and tin oxide, because with flame, you can mix, as long as they dissolve in a solvent, you can mix different precursors, and then you can create a composite. So we created zinc oxide, tin oxide composite. We expose it to the ligand, and only zinc oxide is reacting with that ligand. So you end up with a tin oxide film, which has big chunk of ZIF8 inside. And again, this is just one example. You can actually play with them. You can play with the metal oxide. You can play with the ligand and do whatever it suits you. Again, this is from the side view. So it's extremely porous. The base is tin oxide, but then in the middle, you can actually see as a composite, it has all these ZIF8 embedded into the system. Again, you can also do it at the bottom layer is tin oxide. The top layer was zinc oxide exposed to ligand. The bottom layer didn't change at all, but the top layer is converted to ZIF8. Lastly, what we do is that we use flames pyrolysis as a seeding process to create seeds on the top of, again, literally everything. What you see here is a fiber, is a polymeric fiber being exposed to flames pyrolysis for 1 second, and you see all those tiny. So this is my undergrad student, so the quality of this image is not very high, but you can see all these tiny zinc oxide seeds. Then he put them in a solvent, hydrothermal, and he grow all these nanorods from the fiber. In some cases, he kept the fiber, but in other cases, he put the fibers in the oven. He decomposed them and got rid of the polymer inside. Then by changing the size of the polymer, he actually created this hollow, which we are working with a collaborator on drug delivery, but he can manipulate the fiber, the size of the fiber, make it bigger, make it smaller. You can also change how the nanorods are growing on the surface. And that is on the fiber, but actually you can do the seeding on the top of any even deposited film. There is a tiny film deposited here on the substrate. He does the seeding on the top of that, and then he grows the nanorods on the top of that one. So this is my team, my brilliant team. They're different expertise for different, they do different application. But as I said, if you want to summarize it, wrap it up under one big umbrella, we are very keen to grow and synthesize a wide range of nanomaterials and a wide range of nanostructure. The application usually depends on what is available or what is our collaborator wanted to do. Thank you.
Thank you very much, Noushin. So we have plenty of time for questions. I'll start with the people in the room, but people online, I will not only give you a chance to unmute and ask questions in a moment, but you may also add a comment to the Zoom and I can read that out if you don't want to unmute yourself. So starting with the room, I mean, I can hand it over to you, Noushin, for the questions in the room. So
No worries. Yeah.
go ahead. Yeah.
Maybe I'll go a little bit more fundamental question around the aspect you showed where you could use ethanol to actually condense the nanostructures. Well, I guess my question is, do you see this effect being varying across solvents with different surface tension? Ethanol has a lower surface tension. Would you think that you'll have, some sort of scaling analysis with different surface tension?
Absolutely. Yeah. So we try a wide range of liquids. For example, water, regardless of how many optimization we've done, never worked. Always damage the surface. Sometimes even at the very, very front part of like very close to the droplet, it even washed away the particles. Methanol worked in a way that has less significant impact compared to ethanol. So the change or the clusters are a bit, the gap between the clusters with methanol is smaller. With ethanol, I think that is evaporation. The evaporation is pulling them from each other. So then with ethanol, you get a bigger gap between these clusters. With methanol, you actually have a less. We tried DMF, we tried toluene. Toluene worked very well. And then I would say maybe different liquid for different structure and also different liquid for different metal oxide. So then we kind of optimize that from that perspective. You can also change the evaporation time. Like if you do it on a heater, you evaporate it much faster. You would end up with slightly different structure. And also, if what type of the droplet, we've done all the way from 1 microliter, it's the same size of the sensor film, all the way to 10 microliter. Yeah, and then there is this, it's not, oh yeah, look at this one. Like I think this one is water. If I recall it, or it's something that I would consider it as not working because this is kind of damaged, and then in some cases it was washed away. But this one is a very small droplet, so you can see this section didn't change because the droplet was not enough to actually cover the whole area. But that section changed a little bit, but even that change is kind of different in terms of structure compared to the clusters.
Thank you, Noushin. I also want to point out that, in maybe early 2000s, there was a lot of work on nanotube forests. And this technique was used to make patterns.
Patterns, yes.
Where you kind of break the van der Waals forces to some extent with surface tension. And then as it evaporates, you bring them together. There has been I think a significant number of papers in that area. Also, one more comment I wanted to make. I want to commend you on the applications you have chosen. I really appreciate that someone in Australia is trying to go to the agtech sector. It's probably an area where there's a lot of opportunity, but I'm so glad that you have taken on the lead in that area. Thank you.
Thank you. Yeah, regarding the papers you mentioned, I totally agree with you. What I found in the literature, because the first time we figure out that this is happening, and it was all by accident. So he was washing one of the glasswares in the lab, one droplet dropped there, and they're just like, oh, the transparency changed. We check it, and all the way, that's the story. But back then, we did the literature to make sure that there's a novelty involved. We couldn't find a film, but they were like a nano wires or nano rods as a kind of a growing on the surface, and then they put a droplet. and then these are bending into each other and create that patterns, yes. And then based on what is the distance between the nanowires, they kind of bend it towards the neighbor one or bend it towards this one, yes.
Thank you.
Brilliant talk. Thank you very much. And
Thank you.
Very, very cool technique. I missed the very first part, and maybe my question, you already said it. I was wondering, in terms of the particle material, what range of particle material you would be able to use? And also the second question is, I think in some of the pictures you shown when you show the side view, the thickness of the film, I guess based on the application you're currently targeting is like 10, 20 micron.
Yep.
But I'm wondering, can you then go down to like a much thinner coverage and then use this to do, as you mentioned, like nanowires or those type of structure for surface enhanced sensing type of methods, which it's a different application, but I think could be very interestingly fit here.
Sure, yeah. So the first question, in terms of the particle size, we can go down to 7 nanometer. I struggle going smaller than that, but I have to tell you, it's not a monodisperse. So when I say 7 is the smallest one. The average is around 12 in that batch of 7. So it's somewhere from 7 all the way to like, I don't know, 15, 16. And that's the smallest one. But then the challenge will be sometimes when they are too small, they merge with each other and you end up with, again, a very kind of welded, agglomerated nanoparticles. It is possible to solve that problem, but then you wouldn't end up with, I would say, like 5 micrometer of a film in a minute. You have to do it slowly. You have to like spray maybe in 20 minutes in order to create the same film, but then you control that, you kind of prevent the particles to join. So the challenge is that it is polydisperse, but you can change the particle size simply feeding rate. You change the feeding rate, you change the concentration, and you reduce the pressure, the oxygen pressure when it's heating the droplets. If it's high pressure, the droplets are going to be significantly smaller. You end up with smaller particles. And then if the pressure is less, then you're going to end up with bigger particles. Your second question, we can go as thin as you want. We can actually, that's why we're using it as a seeding process. We can go with like a 1 second and done. The only thing is that you might not have, so when you spray long enough, you get a thickness. I mean, this is very thick. Usually we work around 7 micrometer, but 7 micrometer is equal of 115 nanometer thickness, because when I say 7 micrometer, is a 7 micrometer of 98% porosity film. So the material over there is actually 115 nanometer. But then when you go very, very thin, then you might end up with nothing, 1 particle, then 2 particles, then 1 particle. So if you're okay with that, you can literally do 1 second. You can do 10 seconds. It gives you, let's say, like 300 nanometer. So yeah, you have all this luxury of what thickness you want, what porosity you want, and what particle size you want.
And then just one follow-up question. Then
Yes.
Can you also apply this to like material like with plasmonic effect, like silver or gold or things like that?
We can. With silver, there is a little bit of a bit tricky. Sometimes it get oxidized inside the fire as well. With gold, platinum, palladium, we tried. Absolutely not a problem. Yeah. Yes. With silver, we ended up with both silver and silver oxide.
I was asking because when I see those branching 3 that you're forming, that's going to be an amazing like enhanced surface,
okay.
right?
Yep. Haven't tried that. Haven't tried it for that application. So yeah, happy to do so. Yep.
Hi, Noushin. Thank you for the talk. I'm interested in the particle welding, the cold welding process.
Yep.
Do you know what's actually occurring between the particles? Is it just they're being squashed together? Is there chemical bonding occurring? And kind of related to that is, does that welding process change with the age of the film?
Okay, so there is a little bit of both. Again, this is what we're seeing. We've done FTIR and we realized that, yes, there is a little bit of a kind of, okay, so I think, and that's why one of my students is doing MD simulation. I think there is 2 processes happening over there. The first one is the force, definitely, and it's kind of forcing them to weld. But the other one is, again, this is what I hypothesis. I think that the atoms over there in the structure, because of that condensation of the solvent, they receive a little bit of freedom to move around. Because again, with the vapor, we tried with different vapors, and it didn't work with all of them. Like in zinc oxide, it worked beautifully with acetic acid, and I think it's because zinc has a little bit of the solubility, yes. But then if you try, we hold it above the kettle when it's boiling, this water, it didn't work. Exactly the same as it was before.
Measurements of
Yes.
TA versus TM. I can see the TM on B, but why not TM on the A? Right?
Oh, yes. Yes. So I think I'm not showing it here, but yeah, we do have the, okay. So
most of the solvents
for coming.
capture the
Yes, so the TM you see here is not valid. Why? Because in order to do this TM, we collect the particles from the flame-made sample, and then we dip it in the liquid, which is ethanol again, to do the TM. So then to me, that was not really a way to see whether they are connected or not. What we did, we hold the TM grid directly above the flame. So then we deposited the particles directly on the TM grid without any influence from the TM sample preparation, which has the ethanol involved. The particles are completely separated. Like when they sit next to each other, you can, under the TM, I might have it in my extra slide, but I'll have a look. But they kind of just touch each other. There's absolutely no connection. So when you do the fringes, and you can see that they are completely in different orientation. Yes.
So I guess the second part of that was, does that cold welding process change if you age the as coated films before adding the ethanol? So, you know, for example, the surface chemistry is changing over time depending on the environment.
I don't know. Yes.
Because it might help understand what's going on. Like,
So what do you mean? Like you
age the film, for example, exposed to air, which you might do by
over
accident,
time, is it?
and then try and do the ethanol welding. Does it work?
Okay. Okay. We have to try.
Someone must have accidentally tried that.
Yeah, but maybe we never noticed it. Yes.
It doesn't work.
Yeah. No, good point. Yeah, very good point.
Maybe I can add a point about that cold welding process, because in the field of ceramics, I've done a bit of piezoelectric ceramics. There's a process called cold sintering.
Yep.
And that process involves mixing particles with minute amount of acids. And by cold sintering, they mean sintering at low temperature, like 200, 300 degrees versus 1,200, 200 degrees. And that acid helps with dissolving the boundaries, the surface of the particles, and then facilitates diffusion, and then later welding when the whole thing dries.
Okay.
I think that's why when you use acetic acid droplets, that facilitates a similar process.
Yeah. So the key here was that to not destroy the structure, but also at the same time improve it, or at least the structure stay the same, which in the case of the vapor, the structure didn't change significantly. Like the structure, yeah, a little bit in terms of the transparency, but in terms of the morphology, macrostructure is very similar. It's just like a bit shrink, but didn't change. But we still got a significant improvement in terms of connection between the particles. So that welding happens because of the condensation and force. Yeah. Yes. No worries.
So your film deposition method is a flame pyrolysis method.
Yes.
What are your thoughts on, because I do have a thought process on thinking about, I guess, is it scalable? How scalable is this method in terms of, because when you make sensors, you have to think about, less than a cent deposition methods, right? And repeatability across sensors. What are your thoughts on,
Yep. Sure. So in terms of the technique itself, it is scalable, and I know that people are using it not necessarily for sensing, but for creating coatings, for creating particles. And the flame in the industry is not, so for us, the flame is like 8 centimeter, 6 to 8 centimeter. The one in the industry is huge. I've seen one of them, and like the particle collector is here. It's like a 1 meter. That's the size of the film. The possibility of scalability, you can, like one of the substrate holder we have, the substrate holder is actually moving. So then, I mean, we deliberately created in terms of go back and forth because we wanted to coat a large area. But I can imagine the same scenario would be valid if you have the coating just, you know, on a kind of like a rail and just like coming and then going, and then you kind of change the speed. And then based on that, you can change the thickness. In terms of reproducibility, we don't do that, but I'm aware that some people they do measure the resistance of the film during the deposition. And once it reached to the certain resistance, they cut it. So then they kind of can guess that this is the same thickness. We don't do that, yeah.
One more question to scalability. I'll be more worried about scalability of the ethanol processing, if we can call it.
Yes.
And how much you're going to put, and how are you going to repeat the same structure every time? What's going to happen there?
So if you are dealing with a 1 centimeter square, every time is the same. But the reason that we actually wanted to do vapor is, again, a scalability. So the scalability for vapor is very, very possible. Imagine that you have meters of coating, and they go into the chamber, which are all the vapor, and they just get out of the chamber. So they can, again, they can be on like a roll, go there 10 minutes, 5 minutes, and then get out of the chamber, evaporate, and done. But in terms of the ethanol droplet, yes. When we make the film bigger, like this size, we had to do 10 droplets all around. Then we realized that the middle one is still not being impacted. Then what we did, we put a syringe pump, and now instead of putting a droplet, we very slowly feed it. It didn't work, no. I mean, we're still trying. We're still trying. This is what happened like 2 months ago, even though that the first paper published 2 years ago. We're still trying, but we still have problems with the scalability of the ethanol droplet.
We have one question online. I'll just read it out. How selective are the MOX gas sensors you show? How do you deal with selectivity for detecting pregnancy in cows, considering that breath comprises of multiple molecules?
Absolutely. So they are not selective if you use them as a metal oxide only, for sure. If the metal oxide, for example, let's say tin oxide, is sensitive to almost everything. So that's not a good sensor. But then we do functionalization. One of the reasons that, for example, we've done ZIF8 on the top of tin oxide because we wanted to make it selective towards methane. And that was also industry interest. In terms of so we have to do more functionalization. Even you do functionalization, it depends on what environment. It's still not selective. Then you have to do arrays of sensors. In an industry, they know that there are 16 biomarkers for pregnancy, but we're not doing all the 16. We're only trying to detect 5, the top main one, which significantly change. And then we leave it to the data analysis and AI in terms of writing an algorithm that can tell you with a high accuracy that whether the cow is pregnant or not, if we can detect these 5. And that is the project, that is my industry, ARC industry. So we've done some pilot study in order to proof of concept, but we still have another 3 years to do that.
Just give an opportunity for people online to unmute, hopefully in an orderly fashion, unmute to ask any questions. I'll just give them a moment to do that.
Pregnancy testing.
Sure.
Are you using any time separation before the detection, or is it just a single sensor exposed to the entire sample at one go?
Okay, so the way they're gonna do it, based on my understanding, is that they have like a chamber or something. They ask the cow, they guide the cow to come over here, and then the cow is gonna be there for a couple of minutes, and then they're gonna do the breath test and leave the cow, and then we're gonna have a little bit of a off time for the sensor. That was your question, was it?
Not about the cows, it's more about the sample, like the breath sample. Is there any like separation, like chromatographic separation, or is it just the sensor is exposed to the whole sample at the same time?
I understand. So they do use some of the filters, but without, except to the filter, no, it's going to be the breath. So the filter is just going to make the breath to be a bit cleaner. We do have a tiny heating chamber again, for cleaning the breath before going there. But yeah, in addition to that,
It's a broad
this is-
spectrum sensor.
Yes, yes. But then it's going to be designed in the way to functionalize, organically functionalize. So the sensing element itself is an inorganic material, functionalized by an organic material, which can bond with a particular biomarker. Yes.
So just give a moment for people online. If you want to unmute, please do so and ask a question to Noushin. No questions online?
Oh, there's one question in the room.
We'll go back to the room then.
Thank you for a nice presentation. I have one question regarding the substrate.
Yes.
So is this always going to be glass, or can you put on some other substrates, the same methodology?
We can deposit on anything. We can deposit on a piece of paper. Let me go back to some of the example here. And I have some of the coatings here on even a paper. You can deposit it on a plastic, on a glass, on a ceramic. Once I even coated my shoe, like I made it hydrophobic, so it didn't get, it worked for 8 months. But yeah, you can actually deposit it on anything. It just depends on the thermal stability of the substrate. You might need to enhance the water cooling, slow down the spray time, so then the flame is going to be shorter, so then it's less heat, or put it a bit far. There are some optimization involved, but as long as you wanted to have metal-oxide, carbon dot, and noble metals, we can do it on any substrate.
Oh, yeah. The second question I had was like, when you scale up these, it's going to be outside anyway, like in bigger scale. Would that introduce any defects like stoichiometric defects in your metal oxide?
Yes, it does. We do like in terms of the defect, in terms of like vacancies you're talking about. Yeah. So the material has a lot of defects. Yes.
Is there any should be a tight control of that for functionality, or is that?
You can control it, but sometimes we prefer that defect. It works in our favor.
Okay.
Yes, but you can. Again, like for example, oxygen vacancy is one of the main defects we get in these films. Of course, if you want to minimize it, you can provide more oxygen. So the setup, if I show you, okay. So in this picture, if I show you the setup, there is a porous ring around the setup, which we're not really using it, but there's option available. And that one can be, so the structure is porous here, is a metal, but it has extremely small porosity, pores, and then can be connected to, let's say, nitrogen. We call it like a sheath gas. So you can kind of cover your flame inside a protective gas, or you can use it oxygen again. You can provide even extra oxygen if you want. Currently, we're not using it. As I say, most of the application, the defect is in our favor. We wanted to have that. Yeah.
Thank you.
No.
A nice presentation, Noushin. I guess your emphasis is not here for stability of these coatings, because mostly your applications are on sensors. But if you want to make stable coatings on, even not on large scale, but whatever you are using in your circumstances, how stable they are, and what are the parameters that you choose to make them stable?
Sure. So in terms of stability, if you modify this structure into this structure, the dead forest one, this one is pretty stable, but it depends on how you define stability. For me, the stability, if I dip it into the water, is it collapse or not? Can I make a sensor that can work under the water, like a UV sensor? Can I have it on the watch and then or on the sunglasses, and the swimmer can jump into the ocean and the sensor stay there? Yes, this one you can. If in terms of stability, you mean you have a blade and you want to scratch the surface, no, it's not.
Or just the pencil test, they have black or HB or different levels of HB in terms of like standard coating stability
I understand.
test.
So if, okay, the harshest scenario we tested, we had it into the water and we had the water circulating. And then we changed the circulation like a speed, like a pressure, and it was still okay. Yes, correct. Yes, it's a functional coating. Yes.
Mm-hmm. And just on separate, have you tried like, first you do your what you call cold welding with whatever solvent it is, and then you do another layer and see what happens to those structures, or maybe that's not your massive, but have you tried that? What happens there?
We tried it on this structure. Let me show it to you. Okay, so this one at the bottom is cold welded. So we have the tin oxide, then we have it cold welded. That's why it is not that porous as you would actually see in a flame-made film. Then we added zinc oxide on the top. We didn't cold weld the zinc oxide, but then we changed it into ZIF8. Yes, you do have that kind of a flexibility of multi-layers. You can go up to as many layers as you want. And then you can do all the processing you want on the bottom layer and then see what you can do on the top layer. So it's a completely different. Once you do this cold welding at the bottom layer, to my understanding, that is not going to change anymore. That's very solid. The next process is not really changing. So you can actually create that one, then add the second layer and do whatever you want on the second layer. Yeah.
Okay, one more call out to those online. If you want to unmute, it's going to be the last question. Time to make your mark. No? Okay. One more round of applause, please, for Noushin.
Thank you so much.
Thank you very much. It's been a great pleasure, and thank you everyone in the audience. Have a great day. Thank you.